Imagine we have two locations in space. Location 1 specified by the coordinates x sub 1, y sub 1, and z sub 1, and location 2 specified by x2, y2, and z2, both in the same coordinate system. All right, for many reasons, it's useful to construct what's known as a separation vector pointing directly from location 1 to location 2, and whose magnitude is the length of the straight line distance from location 1 to location 2. So we'll call that the separation vector from location 1 to location 2. We could represent it with this notation. Later we may drop some of the subscripts when the context is clear. All right, so the separation vector from location 1 to location 2 will have components that are equal to the differences in the coordinates. So delta x will be x2 minus x1, delta y would be y2 minus y1, delta z would be z2 minus z1, if we're talking about the separation vector from location 1 to location 2. All right, so basically this is our three-dimensional vector representation of that separation vector. From there we can get the magnitude of that separation vector. We can represent it this way or this way, and the magnitude is constructed basically using the three-dimensional Pythagorean theorem. That is the square root of the sums of the squares of the appropriate components. All right, once we have those things, we can get a unit vector. That's just the directional part of the separation vector, and for many reasons this is an important vector to construct as well. So when we're constructing the unit vector corresponding to the separation vector, we use for the symbol the little caret on the top to represent the unit vector. And we can construct the unit vector by taking the original vector and dividing by its corresponding magnitude. Running that through, if we want to look at the components of the resulting separation vector, those components will necessarily be as follows. And then this is the three-dimensional representation of that unit vector corresponding to the separation vector from location 1 to location 2. All right, before doing a concrete example of this, I want to note that, of course, given any two locations in space, there's actually two separation vectors we could construct. We could construct the separation vector pointing from location 1 to location 2. That's what I just worked through here. We could also construct a separation vector pointing from location 2 to location 1. If we want to clarify that context, we just switch these around. We'd switch these subscripts, and that would mean that our delta x would be x1 minus x2 if we're going from location 2 to location 1 with our separation vector. Again, so noting that the separation vector from location 2 to location 1 will be the negative of the separation vector from location 1 to location 2. That is, those two separation vectors, they're in opposite directions, but they'll have the same magnitude. Okay, so now let's do an example. In this example, let's imagine that location 1 has x coordinate of 3 meters, y-coordinate of -2 meters, and a z-coordinate of 1 meter, and that location 2 is specified by x equals 4 meters, y equals 6 meters, and z equals -2 meters. We can now construct the separation vector. Delta x, which is x2 minus x1, will have 4 meters minus 3 meters. That'll give us 1 meter. Delta y is 6 meters minus a -2 meters. That will give us 8 meters. And delta z is -2 meters minus 1 meter. That gives us -3 meters. We can plug these components into here to get the magnitude of the separation vector. And finally, we can plug all this in to get the unit vector corresponding to that separation vector as follows. Boom. I'm not going to bother to reduce the square root of 74. And also note that really I had 1 meter over the square root of 74 meters, and the meters and meters canceled. And that happens in the other components of the unit vector as well. The unit vector should be a dimensionless vector, and the magnitude of this should be 1. So you can verify to yourself that this squared plus this squared plus this squared, add those up, take the square root, that should be 1. I'll leave that for you to verify. So I hope this example has been useful. We'll be using both the separation vector and unit vectors corresponding to separation vectors in our study of electric and magnetic fields. Thank you.